Hi, everybody. So now we're going to look at a very basic theorem in group theory called Lagrange's theorem. Lagrange's theorem says that if you have a finite group and you have a subgroup of that group, then the number of elements in the subgroup has to be a divisor of the number of elements in the group. And this is a very powerful constraint on the structure of groups and allows us to just do a lot about groups without really knowing that much about them. So we're going to start by just looking at the statement of this theorem, Lagrange's theorem, and then some examples to see if we have reason to believe that it might be true. So just to state things formally, suppose G is a finite group and H is a subgroup of G, then the number of elements in H is a divisor of the number of elements in G. That's called Lagrange's theorem. And let's look at some examples. And let's start by looking at the symmetries of the equilateral triangle. This is a group that we've seen in several different forms. We've seen it as the symmetries of an equilateral triangle. We've seen, and therefore as the dihedral group, D3. Remember, we looked at symmetries of regular polygons, and the equilateral triangle is the simplest one. And we've also seen it in the form S3 as the symmetric group on three elements, or all because if you look at the symmetries of the equilateral triangle and you look at the vertices, every possible permutation of the vertices corresponds to a symmetry of the triangle. Namely, you have the rotations, well, you have the trivial symmetry, then you have the rotations 1, 2, 3, which takes you this way. And if you do it twice, 1 goes to 3, 3 goes to 2, goes to 1. So I'm using cycle notation here. And then you have the reflections, which hold a vertex constant and flip the other two. So we have 2, 3, 1, 3, and 1, 2, corresponding to the three reflections. And those are the 6 elements of this group, which has sort of 3 different names, or at least it comes up in lots of situations. So it's a group of order 6. So what are its subgroups? Well, we can start by looking at the sort of obvious subgroups that we see. The first is the trivial subgroup, which just contains the identity element. Never forget about that one. That has 1 element. Then there's the group itself, which has 6 elements. A group is a subgroup of itself. And of course, 1 is a divisor of 6 and 6 is a divisor of 6. This isn't very interesting, but it's consistent with what we want to be true. And now, if we take the other subgroups, well, one other subgroup is the subgroup that just consists of the rotations. So if we take the subgroup of rotations, that has 3 elements. If you do a rotation, and its inverse is also a rotation, and if you do the rotation twice, it's still a rotation. So that's good. And then, of course, we also have a subgroups of order 2. If we just take the identity element and one of the reflections, let's say 1, 2, that's a subgroup of order 2. Or we could have taken 2, 3, or 1, 3. Each of those are subgroups of order 2. So there are subgroups of order 2. So if this is H, and this is the number of elements in H, you see that all of the numbers which occur as orders of subgroups are divisors of the order of the group, which is 6. How do we know there aren't any other subgroups? Well, let's suppose that H is a subgroup. Well, if H is not the identity, not the trivial subgroup, then either H contains a rotation or a reflection, because those are the only possibilities, right? If you have a subgroup which is bigger than just the identity element, then it either has to contain one of these guys or it has to contain one of these guys. So suppose it contains a rotation. This is going to be a sort of analysis by cases, and what we're going to show is that if we have a subgroup, either then it's already on our list. So if it contains a rotation, then either, so let's call these groups A, B, C, D. H is case C, meaning it's just all the rotations, or H also contains a reflection. So in other words, if H contains a rotation, then either it's all rotations, or it's what happens if you have the rotations plus a reflection. So let's imagine if H contains the rotations, and let's just say if it contains a reflection, maybe 1, 2, well, then H also contains the product 1, 2, 3, 1, 2. And if we use our ability to multiply cycles, here 1 goes to 2, and then 2 goes to 3. So in the end, 1 goes to 3, and then 3 goes back to 1. So if H contains 1, 2, 3, and 1, 2, it also contains 1, 3. And if H contains 1, 2, 3, and 1, 3, so let's say 3 goes to 1, and then 1 goes to 2, so 3 goes to 2, and 2 goes to 3, then it also contains 2, 3, and before you know it, we see that H is equal to G because it contains the rotations and all the reflections. So if our subgroup contains only rotations, then it's case C. If it contains anything else, then it's case B. It's all of the group. And if you want to do the same kind of argument, suppose that if H contains a reflection, like 1, 2, well, then you're either in case D, or if H also contains a rotation, 1, 2, 3, or 1, 3, 2, and then we just showed that if you have a rotation and a reflection, you're the whole group. And in that case, so it's all of G, or it contains another reflection. Like 1, 3. And but then, if you look at 1, 2, 1, 3, this is 3 goes to 1 goes to 2, 2 goes to 1, 1 goes to 3. In other words, if you contain 2 reflections, you contain a rotation, and we already know that if you contain a rotation, then you can enter a reflection, then you're the whole group. So therefore, again, H equals G. So these are all the subgroups. If you try to make any of these subgroups bigger, they fill up the whole group. And they all have order which divides the order of the group 6. Okay, let's look at a few other cases. What about the group Z12? So this is an abelian group. It has 12 elements. What do we know about the subgroups of this group? Well, we actually know quite a bit about them because this is a cyclic group, and we know that every subgroup of a cyclic group is cyclic. Let's just see if we can list them. We know that from our work on cyclic groups. So let's take the possible cyclic group generated by a subgroup of this group. So we could take if you take the group generated by 1, that's all of G. If you take the group generated by 2, well, that's the group 2, the subgroup 2, 4, 6, 8, 10, 0 contained in G, which has 1, 2, 3, 6 elements. If you take the group generated by 3, that's 3, 6, 9, 0. That has 4 elements. If you take the group generated by 4, you get 4, 8, 0, which of course has 3 elements. And if you take the group generated by 6, it has 6, 0, which is 2 elements. And so these subgroups all have order that are divisors of 12. And this is all the possibilities. And why is that? Because we know that if you take the subgroup generated by A, the order of this is the smallest n, so that n times A is divisible by 12. And that number is, if we take the greatest common divisor of 12 and A, it's 12 over the greatest common divisor of 12 and A. So for instance, in the case of 2, the greatest common divisor of 12 and 2 is 2, and 12 over 2 is 6. The greatest common divisor of 12 and 3 is 3, and 12 over 3 is 4. And it's clear from just looking at this formula that the number of elements is always a divisor of 12, because the number of elements, n, times the greatest common divisor of 12 and A is 12, so it's a divisor of 12. So Lagrange's theorem is true for these cyclic groups that we've looked at. Let's look at some other examples. What about the symmetric group on 4 elements? This is a little bit more complicated group. It has 24 elements. It's hard to list all the subgroups. I'm not going to try like we did with S3. That's kind of a long argument, but at least we can look at the elements. So the elements are of the following kind. There's the trivial element. It has order 1. There are the transpositions. They have order 2. There are the 3 cycles. They have order 3. There are the products of disjoint transpositions. They have order 2. Because when you multiply disjoint transpositions, remember that they commute with one another. So 1, 2, 3, 4 times 1, 2, 3, 4 is just the identity. And then there are the 4 cycles, which have order 4. So the orders of elements divide the order of the group. And that's a consequence of Lagrange's theorem, because the order of an element is the number of elements in the cyclic subgroup generated by that element. And by Lagrange's theorem, the number of elements in the subgroup has to be a divisor of the number of elements in G. And we saw one other interesting example of a subgroup of S4, which was the alternating group, the subgroup of even permutations. And the even permutations consist of the identity element, the products of disjoint transpositions, of which there are 3, and the 3 cycles, and this group altogether turned out to have 12 elements, and 12 is a divisor of 24, so that's consistent with Lagrange's theorem. And then maybe, I think the last example I wanted to look at is, we know one other subgroup of the symmetric group on 4 elements, which is the dihedral group, the symmetries of the square. So you remember the symmetries of the square, if we label the vertices 1, 2, 3, 4, then the symmetries of the square are given by the rotation. This is D4. We know this has 8 elements, but I'll just remind you what they are. There's the rotations, of which there are 3, except 3, you can turn the square once, twice, or 3 times. There's the identity element, which is if you don't turn the square at all. And then there are the reflections. There are 2 like this, and 2 reflections like this. And if you want to think of these as permutations of the vertices, the identity element, of course, is the trivial permutation. The rotations are cycles. The reflections across the sides are disjoint transpositions, you see, because if you reflect along this axis, you interchange 2 and 3 and 1 and 4. And the reflections along the diagonals are just transpositions. If you reflect along this diagonal, for example, you interchange 1 and 3. And that's how you can think of these as permutations. But the main point here is that this group has order 8, and 8 is a divisor. It's a subgroup of S4, and 8 is a divisor of 24. Maybe I should conclude with just one comment, which is the converse of Lagrange's theorem is false. It's not true that if you have a group, let's say you have a group of order whatever, 60, and you have a divisor of 60, it's not true that every group of order n must have a subgroup of order d if d is a divisor of n. And we'll see some examples of that later. So it only goes one direction. If you have a subgroup, then its order has to be a divisor of the order of the group. If you have a divisor of the order of the group, you don't know for sure that there necessarily is a subgroup of that order.